Hello again, physicists. It's good to be back. In class, the last couple of days, we have been creating various interactions, collisions between two different objects, and observing and recording data related to their individual momentums. And then, ultimately, the last thing I asked you to do was look at their combined momentum before and after they interact with one another and see how they compare. And the truth is, we should have seen that regardless of the type of collision we had occurring, no matter what parameters we changed before we tested out our collisions, the total momentum in each case before should have been equal to the total momentum afterwards. And what you were observing there was what we call the conservation of momentum, which states that the total momentum of a system immediately before and after an interaction is conserved. Mathematically, what that means is if I take the sum of all the individual momentums before an interaction occurs initially, it has to be equal to the sum of all individual momentums within a system after the interaction occurs. This means that the momentum of the individual objects can change, but the momentum of the overall system cannot. And this is a rule that is true every time, regardless. It's not like conservation of energy, where if there was a non-conservative force, the system would lose energy to its surroundings or gain energy from its surroundings. Conservation of momentum will be applicable regardless of the presence of friction or external forces. Now, when we observe an interaction between two objects, and we are applying the rule for conservation of momentum, there will be three major categories that we can put an interaction under. And the first category is what I call a bouncy interaction. So a bouncy interaction would look like the following. I'm going to give you two different diagrams, two different examples of a bouncy interaction, and then I will let you guys, along with me, implement the conservation of momentum. So the first interaction I'm going to show you will have two objects, object A and object B. And in my first example for a bouncy interaction, object A will have a velocity directed to the right, while object B will be at rest initially. And then afterwards, once they collide, both object A and B will have some velocity directed to the right. So there's a little illustration showing you this interaction and what the two objects are doing before, initially, and then after the interaction occurs. So what would the conservation of momentum look like if we were implementing it for this particular case? All right, well, right off the bat, we can say that the sum of all the momentums before initially has to be equal to the sum of all the momentums after the interaction occurs. So now I have to look at, okay, which of my objects has momentum before they interact, put them all on the left-hand side of my equation, and which objects have momentum after they interact. And I would put all those together on the right-hand side of the equation. Looking at the diagram that I drew, initially, only object A has momentum. So only the momentum of object A will be accounted for initially. And whatever momentum object A has must be equal to the momentum of object A plus the momentum of object B after they interact. Since both of the objects are moving, both of them have a velocity, thus they have a momentum after the interaction occurs. For my second example, showing a bouncy interaction, we're still going to have two objects, object A and B. The difference in example 2 is that now both A and B will have their own momentum before they interact, before they hit each other, and they will also have their own momentum after they've hit each other. So you can imagine this particular interaction almost being like a head-on collision, where two objects are heading towards each other, they make contact, they bounce, and then they rebound in the opposite direction of their incident velocities. What would conservation of momentum look like for such an interaction? Okay, so to start off, again, my momentum for my entire system before the interaction will be equal to the entire momentum of my system after the interaction. So initially, I'm now going to have two momentums being combined initially for both A and B. And I have to be careful because momentum's a vector, so the direction of the momentum matters here. Because A has a velocity directed to the right, that means that it will have a positive initial momentum. And because B is actually got a velocity directed to the left, that means that B will actually have a negative initial momentum for that reason. And that will be equal to the combined final momentum of the two objects, where basically the direction of the velocities will be flipped. Now A will have negative momentum since it's traveling to the left, and B will have positive momentum. So there you go. And you can clearly see that if either initially or finally there's an object that does not have any velocity, it doesn't show up in that portion of the conservation of momentum equation because no momentum means a value of 0. So there are a couple of examples for bouncy interactions. All right, next type of interaction is what I call a sticky interaction. So what will a sticky interaction look like? For my first example, we still will have two objects, and initially it's going to look a lot like my first example from when I was showing you bouncy interactions. So I have object A, which is moving to the right with an initial velocity, so it has momentum, while object B is at rest. However, after the two interact in a sticky collision, they literally stick together. It's almost like they combine to become one single object that moves with a single momentum. So what would the conservation of momentum look like for this example where we have a sticky collision? Well, same equation, adding up all the momentums that I have initially. It has to be equal to all of the momentums combined in my system that I have after the interaction occurs. And before the interaction happens, I have one object with momentum, and that is object A. So initially, the momentum of object A will be equal to the momentum of A and B moving together as one single object. So because they're stuck together, they're going to be treated as one object with a single momentum. And if we wanted to find the momentum for this super object, we would take the combined masses of A and B and multiply it by whatever velocity they were moving at together. For my second sticky example, we will have two objects, A and B, initially appearing to have a head-on collision. And then afterwards, they stick together and come to a complete stop. What will conservation of momentum look like for such an interaction? Well, I know I'm saying it ad nauseum, but again, the combined momentums of both objects initially has to be equal to the combined momentums of both objects after they interact. Initially, both objects are moving, so both objects have momentum initially. The momentum of A will be positive, since it's moving to the right, and the momentum of B will be negative, since it is moving to the left. And afterwards, since both objects come together and come to rest, that means neither of them have momentum afterwards. They combine to make a single object at rest, so I would just put a big fat 0 for the total momentum after the interaction. What this tells us is that A and B would have had to have had equal amounts of momentum initially in order to perfectly cancel one another out when they collided. Okay. Our last example, our last classification will be an explosive interaction. And there's only going to be one example for this. Okay. In an explosive interaction, it's going to be the opposite of what a sticky interaction was. In sticky interactions, you had two or more objects that were separate initially, and then through the interaction become stuck together and make one big object. And in an explosive interaction, you have two or more objects that initially are stuck together, making one big object with a single momentum, and then through an interaction they split apart and become two or more smaller objects that'll each have their own individual momentum. So the conservation of momentum for an explosive interaction, specifically for the case I've illustrated above, would look like this, where initially our big super object is at rest, so there is no momentum before, and then once it splits apart, the final momentum would be the negative momentum of object A, since it's traveling to the left after the interaction, plus the positive momentum of object B, since it's moving to the right. And again, what this is telling us is after A and B split apart from the explosive interaction, they must have equal momentums that are directed in opposite directions. That's the only way that we could have no combined momentum initially, as well as no combined momentum finally after the interaction. So before I leave you, just a couple pointers to remind you when you're using conservation of momentum. First thing is that we are dealing with the total or the combined momentum is being conserved. Again, the momentum for the individual constituents within the system, they can have a change in momentum, but the momentum for the entire system cannot change. Secondly, watch out for directions. Because again, if something has a momentum that is directed to the left, that means it'll be negative. Whereas if the momentum is directed to the right, it will be positive. So just be aware of those two things and you should be okay. Until next time, physicists, until next time.